This is video 7D for the Year 11 Mathematical Methods course. In this video, we're going to cover the theory behind the tangent function under the topic of trigonometric functions. Specifically, we are going to explore a revision of tan of x and the unit circle, the basic tangent function for x being between 0 and 2 pi, the periodic behavior of the tangent function, the general tangent function, the transformations that map the basic function to the general function, how to sketch a tangent function with various transformations, how to find the equation of a tangent function from its graph, and then we're going to cover some example questions. And so now we've reached the third and final part of our little trilogy of videos, all about working with different trigonometric functions. We started off with the sine function, then most recently we went on to the cosine function, and now to cap this off, we're going to be focusing on the tangent function. Now, as you guys would have seen over the last two videos, the sine and cosine functions shared a whole lot of similarities, not only in how we examine them and then also how we graph them out, but also in a lot of their key qualities, in that they had the exact same period, they had the exact same maxima and minima, they had a lot of very similar qualities, and that therefore made it very easy to transfer all the knowledge that we learnt about the sine function and then just apply it to the cosine function. And as you may have already noticed, a really cool connection about the sine and cosine function is that they are each just the horizontally translated version of the other. So it makes a lot of sense that a lot of their key features are actually very similar. Now, with that being said, unfortunately the tangent function does take a bit of a detour away from everything that we've learnt about the sine and cosine functions so far. A lot of the approaches that we're going to take to graph it out are going to be very similar, but in terms of the actual shape of the graph, its period and everything else, it does take quite a large deviation. However, with that being said, we are still going to approach this the exact same way, so let's cover that now. Now, in order to best tackle the tangent function, we do need to do a little bit of revision from when we first learned about tan. And the key thing to remember here is how tan is actually defined. In that, tan of x is equal to sine of x divided by cos of x. Now, this relationship here is probably the most important thing that we're going to be referring back to quite consistently throughout the rest of this video, and it's because we've already learnt a lot about the sine function and the cosine function, and so now applying both these sets of information to the tangent function is going to be a very logical step forwards. However, very similar to when we analysed the sine and cosine function, let's link this back to the unit circle. And so, of course, what we can recall here is that if we pick a particular point along this unit circle, let's just pick this point here, and then we draw a straight line from the origin to this particular point, and also if we define the angle between the positive horizontal axis and this line to be x, then we know that this particular point has coordinates of cos of x, comma, sine of x. In other words, cos of x represents the horizontal position of this particular point, whereas sine of x represents the vertical position. And so the interesting thing that we can do from here is actually find the gradient of this straight line here, because we know that this straight line starts at the origin, so in other words, it also passes through 0, 0. And so therefore, we can say that the gradient of this line is going to be rise over run. The rise is going to be given by sine of x take 0 divided by cos of x take 0, or in other words, it is equal to sine of x divided by cos of x, which of course we know is given by tan of x. And so therefore, we can also define tan of x as the gradient of the straight line connecting the origin to the unit circle with an angle of x to the positive horizontal axis. And so what we can therefore say is that when we study the function of y equals tan of x, then essentially what we're studying is what happens to the gradient of this straight line as we move around this unit circle. So in other words, the study of the function y equals tan of x is essentially just the study of the tangent of the line connecting the origin to a point along the unit circle as we move around the unit circle. Now, in order to study what the graph of this particular function is going to look like, we're going to pick some key points along the unit circle and then find the gradient of the line connecting the origin to that particular point. So the different angles that we're going to be considering in this case are when x is equal to 0, x is equal to pi over 2, x is equal to pi, x is equal to 3 pi over 2, and then finally when x is equal to 2 pi. Now, when x is equal to 0, we know that tan of 0 is going to be equal to sine of 0 divided by cos of 0. We know that when x is equal to 0, this correlates to this point along the unit circle. And so therefore sine of 0 is equal to 0, and cos of 0 is equal to 1, and so therefore tan of 0 is equal to 0. When we consider x equals pi over 2, we're considering a quarter turn around the unit circle, so this point up here. And so therefore, we can say that tan of pi over 2 is equal to sine of pi over 2 divided by cos of pi over 2, which in this case is going to be equal to 1 divided by 0, which loosely speaking we know is going to be equal to positive infinity, or in other words, undefined. Now, when x is equal to pi, this is going to correlate to a half turn around the unit circle, so we're going to be looking at this point over here. And so therefore, we can say that tan of pi is going to be equal to sine of pi divided by cos of pi. Sine of pi is equal to 0, cos of pi is equal to negative 1, which gives us an answer of 0. When x is equal to 3 pi over 2, this is going to correlate to a 3/4 turn around the unit circle, so this point down here. And so therefore, tan of 3 pi over 2 is equal to sine of 3 pi over 2 divided by cos of 3 pi over 2. Sine of 3 pi over 2 is equal to negative 1, and then cos of 3 pi over 2 is equal to 0, which again is equal to infinity, or in other words, it is undefined. And then finally, when we consider x equals 2 pi, this is the same as a full revolution around the unit circle, so we're going to reconsider this point over here, in which case tan of 2 pi will be equal to sine of 2 pi divided by cos of 2 pi. Sine of 2 pi is equal to 0, cos of 2 pi is equal to 1, which is equal to 0. Now, let's quickly go around the unit circle and make sure that each of these answers make sense. When x is equal to 0, the line that we're going to be considering is this line here. And we can see pretty clearly that this is a flat horizontal line, which has a gradient of 0, and so therefore tan of 0 should be equal to 0. When we consider x is equal to pi over 2, this corresponds to this line here, which has an undefined gradient, or in other words, a gradient equal to infinity. So it makes sense that tan of pi over 2 is undefined, or in other words, equal to infinity. When we have x equals pi, we're going to be considering this line over here, which again we can see is a flat horizontal line, which we know has a gradient of 0, so it therefore makes sense that tan of pi is equal to 0. When we have x equals 3 pi over 2, then we're going to be considering this line down here, which we can see again is a vertical line, which has an undefined gradient, or in other words, a gradient equal to infinity. And so therefore it makes sense that tan of 3 pi over 2 is undefined, or in other words, infinity. And then finally, when we have x is equal to 2 pi, this is just this line over here again, which is a flat horizontal line which has a gradient of 0, and so it therefore makes sense that tan of 2 pi is once again equal to 0. So both from an equation standpoint using sine and cos, and from a gradient standpoint, all 5 of these answers here make sense. And so now what we're going to do is use these 5 pairs of coordinates to sketch the graph of y equals tan of x, for x being between 0 and 2 pi. So, first things first, we know that when x equals 0, then y is also equal to 0, so that's going to correlate to this point here. We know that when x is equal to pi over 2, then y is undefined, or in other words, infinity. So therefore, to represent this, we are going to draw a vertical asymptote when x is equal to pi over 2. When x is equal to pi, then y once again is equal to 0. And then once again, when x is equal to 3 pi over 2, y is undefined, or in other words, equal to infinity. So in order to represent this, we are going to draw another vertical asymptote when x is equal to 3 pi over 2. And then finally, when x is equal to 2 pi, then y is equal to 0. So that's going to correlate to this point here. Now, just by the sheer fact that we have vertical asymptotes, this particular graph is going to look very, very different from our sine and cosine waves. In fact, the graph of y equals tan of x looks like this. So the key aspects here, first things first, we've got x-intercepts at x equals 0, x equals pi, and x equals 2 pi. And furthermore, we have vertical asymptotes when x is equal to pi over 2 and when x is equal to 3 pi over 2. That's why we have this kind of behavior here, 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 and here, because surrounding these asymptotes, the graph must keep on approaching them but never ever touch them. So as I made mention of before, we can clearly see here that this is definitely the most unique out of the 3 different trigonometric functions that we're going to be considering, and this is because this looks nothing like the sine and cosine waves that we've previously graphed. And again, the key things to keep in mind here are the positions of the x-intercepts and also the positionings of those vertical asymptotes. Now, the particularly nice thing about this graph is that without even having to extend beyond 0 to 2 pi, we can immediately see the periodic behavior of this particular function. In that, if I box out this segment of the graph here, and then I also box out this segment of the graph here, we can see that both boxes have the exact same shape. In that, we start off with an x-intercept, we then come up towards a vertical asymptote, then on the other side of the vertical asymptote, we start down the bottom, come back up to another x-intercept. And just from this graph here, we can see that the widths of each of these boxes are pi. Which therefore tells us that y equals tan of x is a periodic function with a period of pi. Now, just to make this a little bit more obvious, I will quickly sketch out the graph of y equals tan of x, but we're going to extend out the boundary points a little bit. So now let's consider the graph of y equals tan of x, for x being between negative 3 pi and positive 3 pi. Now, if we took a very similar approach as what we did up here, with the different values of x and then finding the gradients of the corresponding lines, but then if we extended it out between negative 3 pi and positive 3 pi, we would find that the graph takes the following shape. So if the periodic behavior of this particular function wasn't obvious before, I really hope it is now. Very clearly we can see that if I box up this area here, this area here, this area here, this area, and then this area, each of these segments are identical copies of one another. And once again, we can see that each of these domains have a width of pi units. And so therefore, we can say the following. So as we've already said, y equals tan of x is a periodic function with period pi, and so mathematically we can therefore say that tan of x is equal to tan of x plus pi. So in other words, if we pick a particular point on our tan function, and then we move that point to the right by 2 pi, then we get the exact same point. And so therefore we can extend this even further in saying that tan of x is equal to tan of x plus k pi, where k is an integer. And so therefore all we're saying here now is that if we pick a particular point on our function, and then if we move it to the left or right by pi units, 2 pi units, 3 pi units, or whatever, we are once again going to get the exact same point. Which again, considering the fact that tan of x is a periodic function with period pi, and so therefore it just repeats itself after every pi units, this idea here makes a whole lot of sense. And so the key aspects of the graph of y equals tan of x are the following. First things first, we have x-intercepts at x equals k pi, where k is just an integer. As we noticed with the original graph, and as you probably should have noticed with this graph here as well, all of the x-intercepts occur at an integer number of pi. So in other words, negative 3 pi, negative 2 pi, negative pi, 0 pi, 2 pi, and 3 pi. Now this is consistent no matter how far you go in either direction, that as soon as you have an integer number of pi, then there will be an x-intercept there. And furthermore, we can also notice the fact that the vertical asymptotes always occur right in the middle of each of these x-intercepts. We notice that we've got one here at pi over 2, then 3 pi over 2, then 5 pi over 2, then negative pi over 2, negative 3 pi over 2, and then finally negative 5 pi over 2. And so we can therefore generalize this finding to the following. That we have vertical asymptotes at x equals pi over 2 plus k pi, where once again k is just an integer. And so once again, all this here tells us is that these vertical asymptotes always occur right in the middle of each of these x-intercepts. And now another really important distinguishment between the graph of a tan function and then our previously studied sine and cosine waves is the fact that the tangent function does not have a principal axis, it does not have an amplitude, and it does not have maximum or minimum values. Now let's quickly go into why this might be. Now let's start off with the maximum and minimum values. For this particular graph, we can very clearly see that we do not necessarily have a maximum point in which the tan function reaches, nor a minimum point. And that is because of these vertical asymptotes. In other words, the closer we get to these vertical asymptotes, the graph just keeps on getting bigger and bigger and bigger in this direction, or smaller and smaller and smaller in that direction. And so because of that, we can't really define a maximum or a minimum value because we just either keep getting bigger as we get closer to the asymptotes or we keep getting smaller as we get closer to the asymptotes. And so therefore, because we don't have a defined maximum or minimum value, we can't define an amplitude because we know that the amplitude is calculated by taking half of the distance between the maximum and minimum values. So if we can't define our maximum and minimum values, then we also can't define our amplitude. And then finally, we also can't really define a principal axis. Now the reason why this is because when we initially looked at principal axes in the sine and cosine chapters, we defined principal axes as the horizontal line in which the wave oscillates. So in other words, if we have a sine function that looks like this, then we can very clearly see that this wave oscillates around this horizontal line. We don't really have the same type of behavior when we're talking about the tangent function, because in this particular graph, it isn't really oscillating, it just keeps getting bigger and bigger and bigger, then you move over to the other side of the asymptote, then you start all the way down the bottom again, and then you just keep getting bigger and bigger and bigger. So there's not really this back and forth up and down motion as we've seen with the sine and cosine function, and so because of that, we can't really define a principal axis. Now, similar to what we did study when it came to the sine and cosine function, we are going to consider different transformations of the graph of y equals tan of x, but the really nice thing here is that considering everything that we just talked about in terms of a lack of amplitude and a lack of a principal axis, it means that the different types of transformations that we're going to consider here are going to be limited compared to what we've already had a look at with the sine and cosine graphs. And in order to introduce these transformations, the first thing that we're going to look at is something called the general tan function, which looks like this. Now, immediately you should see some similarities between this and the general sine and cosine function, namely this b and this minus c. However, one thing that you should notice, comparing this to the general sine and cosine function, is that we do not have a leading coefficient of a, and we also do not have a plus d at the end. The reason for this is because, as we previously seen, this value of a controls the amplitude of the sine and cosine waves, and this value of d controls the principal axis. And as we've just discussed there, these are the two qualities that we can't actually define when it comes to a tangent function. So it means that the transformations of a and d are not applicable when it comes to the general tan function, so we're only going to consider b and c. Now, the nice thing about these two transformations is that they have the exact same effect as when we're dealing with the sine and cosine functions. Specifically speaking, b is going to induce a horizontal dilation by factor of 1 over b. And now, because we know that the basic tan function has a period of pi, then we know that the period of the general tan function is going to be pi divided by b. So once again, you should notice a similarity here between this and the effect of b on the sine and cosine waves. When we consider the sine and cosine waves, we know that the period is given by 2 pi over b, but that's only because sine and cosine have a period of 2 pi, whereas tan has a period of pi. And then secondly, c induces a horizontal translation by c units. The key thing to keep in mind here is that if your bracket is in the format of x take alpha, then this means that we move to the right by alpha units. Whereas if we have it in the format of x plus alpha, or in other words, x take negative alpha, then this means that we're going to be moving to the left by alpha units. And as I previously made mention of, the nice thing about the tangent function is that we're only going to have to deal with these two transformations. And again, this is because the tangent function does not have an amplitude and it also does not have a principal axis. So we can only really consider the horizontal dilation transformation and the horizontal translation transformation. Now, just as a very quick reminder as well, I know I've made mention about this in the last two videos as well, but because it's such a critical thing, I want to bring it up here as well. If you are ever given a tangent function in this particular form here, of y equals tan of 2x take pi, then this does not imply that b is equal to 2 and c is equal to pi, because this function does not take this kind of format here. In order to accurately determine what the values of b and c are going to be, you need to factorize out the coefficient of x. So in other words, we can now rewrite this as y equals tan of 2 multiplied by x take pi over 2. This therefore implies that b is equal to 2 and c is equal to pi over 2. So once again, similar to your sine and cosine functions, be very, very careful to only use trigonometric functions of this format here. Never ever use ones in this top format here. And so now moving on to the different types of questions you're going to be expected to answer about tangent functions. Once again, they're going to be very, very similar to the types of questions you were already asked about sine and cosine functions, but now we're just going to be applying them to the tangent function instead. So the first type of question is going to be to describe the transformations made to a particular tangent function. Then the second one, and arguably the most common type of question, is going to be to sketch the graph of a tangent function from its equation. And then the third and final type is going to be to find the equation of a tangent function from its graph. And so now, similar to what we've done previously, let's now go through the different approaches that you're going to take for these three types of questions, and we're also going to do an example for each of the three. So, the first type of question is where we are describing transformations. And the example that we're going to use here is to describe the transformations which map the graph of y equals tan of x to the graph of y equals tan of 2 multiplied by x take pi over 2. And now, similar to what we've already discussed with our sine and cosine functions, we're going to use a very, very similar template answer as what we used in the last two videos. But now we're just going to have to make some minor modifications, considering the fact that now we only have two transformations to consider. So this is going to be the template answer that you're going to use to answer a question like this. And there we have it. So in this particular case, the template that you're going to use is the graph of y equals tan of x is dilated horizontally by factor 1 over b, the graph's period is pi over b, and translated left or right by c units. So the only things you need to input in this case is the value of b into these two parts, the value of c into this part, and then to determine whether the graph is going to be moving left or right. So let's now apply that to our example over here. And in this particular case, we can see that b is equal to 2 and then c is equal to pi over 2. So for this example, we can say the graph of y equals tan of x is dilated horizontally by factor 1 over 2. And so therefore the graph's period is now pi over 2. And we can say that the graph is translated to the right, because this value here is positive, by pi over 2 units. Let's now move on to the second question type. And so here we're going to be working with questions which starts us off with a particular tan function, and then we want to sketch the graph of that function. And the example that we're going to work with here is the function of y equals tan of 2 multiplied by x take pi over 2. Now, the core thing to keep in mind here is that when we're dealing with transformations of tangent functions, we've got two different transformations that we can be working with. And that is this b value and this c value. Now with this question type here, we will again be taking a very similar approach as to what we've done with our sine and cosine transformations, but now we're going to have to be looking at it from a very slightly different perspective. Because when we were working with the sine and cosine waves, we had a few different points that we had to transform. We had the x-intercepts, we had the maximum points, and we had the minimum points. When we're talking about tangent functions, we can only really consider two different parts: the x-intercepts and the positions of the vertical asymptotes. So, very similar to what we did with our sine and cosine functions, the first thing that we're going to do here is plot out all the important points of the basic function of y equals tan of x. And as discussed, these important points are going to include the x-intercepts and the vertical asymptotes. Then the second step will be to transform these important points in the order of b and then c. Once you've made the transformations on these important points, we're then going to sketch a smooth curve connecting all these important points, making sure we're very careful when drawing near the vertical asymptotes. Okay, so with that being said, let's now use this three-step process to sketch out the graph of this tan function on the domain of 0 up to 2 pi. And so now we're going to plot out all the important points of the graph of y equals tan of x. So the first thing that we know about the graph of y equals tan of x is that it has x-intercepts at x equals 0, x equals pi, and x equals 2 pi. So I'm just indicating those ones there. Furthermore, we have vertical asymptotes at x equals pi over 2 and x equals 3 pi over 2. Now, rather than representing these asymptotes using dotted lines, I'm just going to draw a hollow circle around these 2 points for me to remember that these are where the vertical asymptotes originally occur. Now that we've plotted out all these important points, let us now apply the transformations in the order of b and then c. So in this particular case, the value of b is equal to 2. So in other words, we're going to take all the x-coordinates of these important points and then we're going to divide them by 2. So this first x-coordinate here is just going to stay where it is because 0 divided by 2 is still just 0. And then this x-coordinate of pi over 2 is going to get halved down to pi over 4. So that's going to go here. Then this point here of x equals pi is going to get reduced down to x equals pi over 2. Then this point here of x equals 3 pi over 2 is going to get halved to x equals 3 pi over 2. And then finally, this point here of x equals 2 pi will get halved to x equals pi. So that's our first transformation there, and now the second one is for c equals pi over 2, which means now that we're going to shift all of these points to the right by pi over 2 units. And so shifting all these points to the right by pi over 2 units, we now get the following. And now we want to try and connect all these points with a smooth curve. So the first thing I recall is the fact that I represented the vertical asymptotes with hollow circles, which are here and here. So I'm just going to draw vertical dotted lines to represent these asymptotes. And then furthermore, we can see that we've got x-intercepts at this point here, and this point here. Now, the only problem with what we've currently got is the fact that we only have points between x equals pi over 4 and x equals 5 pi over 4, which means that we now need to extend this all the way from 0 up to 2 pi. However, the nice thing about a tangent function is that we know that it's repeated, so in other words, it's periodic. In this particular case, we can see that when we go up in increments of pi over 4, then we alternate between x-intercepts, like here, to a vertical asymptote, to another x-intercept, to a vertical asymptote, x-intercept, and so on. So therefore, we can say that this pattern is going to continue in both directions. In other words, we're going to have another vertical asymptote here, here, and here. So let's quickly draw these out. And we're going to have another x-intercept here. So let's just draw out this point here. And now by connecting all these important points with a smooth curve, we get the following. And so we can see here that we pass through all the desired x-intercepts, which is great. And we are also approaching all the vertical asymptotes exactly as we should be. So that's the second type of question you're going to encounter. And then last but not least, the third type of question you're going to encounter is where we start off with the graph of a tangent function, and then we want to find the equation of that particular graph. So in order to tackle questions like this, our ultimate goal is to write our function in the form of y equals tan of b multiplied by x takes c. And so our job is to find out the values of this b and this c. Now, let's first of all focus on how we can find this value of b, because we of course know that the period is given by pi over b, which therefore tells us that b is equal to pi divided by the period. So in order to find the value of b, we need to therefore find the period of the graph. There are going to be two very, very easy ways of doing this. We can either find the horizontal distance between two adjacent x-intercepts, or we can find the horizontal distance between two adjacent vertical asymptotes. And then to find the value of c, we're once again going to take a very, very similar approach as to when we dealt with this with the sine and cosine functions. We're going to identify how the x-coordinate of an important point, so whether that be a x-intercept or a vertical asymptote, has been translated from their original x-coordinates. However, we need to be very, very careful in the fact that we also need to consider how the period has also been affected, and therefore how the changed period has also affected the x-coordinates of these important points. And so like I was saying before, you've only got two different constants to find the values of when it comes to questions like this, which comparing this to the sine and cosine functions, which you need to find the values of 4 different functions, it does make it a little bit easier. And surprisingly enough, you'll generally find these types of questions with a tangent function to be much easier to work with than when you're dealing with the sine or cosine functions. Let us now go for an example of this particular question type. So we're going to start off with this graph of a tangent function. Alrighty, so for this particular graph, we have x-intercepts at x equals pi, x equals 3 pi, and x equals 5 pi. Furthermore, we have vertical asymptotes at x equals 2 pi and at 4 pi. So let's start off by finding the value of b. Now we know that b is given by pi divided by the period. In this case, the period is actually going to be quite easy to find because we can either use adjacent x-intercepts or we can use the adjacent vertical asymptotes. However, let's just focus on the adjacent x-intercepts. So we can see that the distance between these x-intercepts is 2 pi, and we can also see that the distance between these two x-intercepts is again 2 pi. So therefore we can say that the period is given by 2 pi. So therefore b is going to be equal to pi over 2 pi, or in other words, 1 over 2. Now let's focus on finding the value of c. And in order to find the value of this constant, we're going to lock into the fact that the first x-intercept occurs at x equals pi. Because we know that for the graph of y equals tan of x, then the first positive x-intercept occurs at x equals pi. However, we know that this graph is also undergoing a horizontal dilation by factor 1 over 2. So in other words, we're going to be undergoing a horizontal dilation by factor of 2. So we can say we are undergoing a horizontal dilation by factor 1 over 2, or in other words, 2. And so what this therefore tells us is that this horizontal dilation stretches out the graph horizontally such that each of the x-coordinates are doubled. And so what this therefore tells us is that after this horizontal dilation, the first positive x-intercept should occur at x equals 2 pi, because we're going to double this x-coordinate. So in other words, our first positive x-intercept should occur at x equals 2 pi. But it actually occurs at x equals pi. So what this therefore tells us is that our graph has been shifted to the left by pi units. And so therefore, we can say that c must be equal to negative pi. And so now bringing together this value of c and this value of b that we found up here, we can therefore say that the tangent function for this particular graph takes the form of y equals tan of 1/2 multiplied by x take negative pi, or in other words, y equals tan of 1/2 of x plus pi. And so now, just to double check this answer, we're going to come over to the graphics mode on our calculator, put in the function that we just found, and confirm that we get the exact same shape as this original graph. So we're going to come down to our graphics mode, and we're going to type in the function of tan of 1/2 multiplied by x plus pi. And we're going to sketch this. We're now just going to set an appropriate viewing window. So I'm going to set this between 0 and 6 pi. And for the y values, I'm just going to set it between -5 and +5. Let's now quickly confirm that x equals pi, 3 pi, and 5 pi are all x-intercepts. So we can go shift trace, and we're going to go pi. And that one there is an x-intercept. We can now go 3 pi, another x-intercept, and we can also go 5 pi, which is another x-intercept, which is great. Let's now also quickly confirm that we get vertical asymptotes at x equals 2 pi and x equals 4 pi. So if we go 2 pi, then we get an error. So in other words, we've got a vertical asymptote at this point. And similarly, if we put in 4 pi, we get another error. And so therefore we have another vertical asymptote at this point. And so just from this, we can be confident that the equation that we have is in fact the correct answer. And so that now brings us up to the end of our little trilogy of videos all about sketching out different trigonometric functions. I really hope you take into account all the very similar aspects between all these videos, especially when it comes to the different types of questions that you're going to get asked, how to graph out these particular functions, and how they all connect to the unit circle itself. Understanding the connection between sine of x, cos of x, and tan of x is a very important thing when it comes to trigonometric functions. So I hope that after watching these 3 videos, you've got a much clearer understanding of these connections, but more importantly, the very similar processes that you're going to use in order to answer these different types of questions. Alrighty, let's summarize what we've learnt today. So in this video, we revised the definition of tan of x in relation to the unit circle. For a point on the unit circle that makes an angle of x with the positive horizontal axis, tan of x is defined as the gradient of the line connecting the point to the origin. We can also define tan of x as sine of x divided by cos of x. We then considered the graph of the basic tangent function. This graph has the following qualities. Period is pi, x-intercepts at k pi, where k is an integer, vertical asymptotes at x equals pi over 2 plus k pi, where k is once again an integer. We then introduced the general tangent function, which takes the form y equals tan of b multiplied by x takes c, where b and c are constants. Both of these constants induce a unique transformation on the graph of y equals tan of x. B induces a horizontal dilation by factor 1 over b. The period is given by pi over b. C induces a horizontal translation by c units. If c is greater than 0, the translation is to the right. If c is less than 0, the translation is to the left. We then explored the three main question types related to the tangent function. Question type 1, describing the transformations which map the graph of y equals tan of x to a transformed function of the form y equals tan of b multiplied by x takes c. To answer these questions, we can make use of the following template answer. The graph of y equals tan of x is dilated horizontally by a factor of 1 over b. The graph has a period of pi over b. Translated to the left or right by c units. Question type 2. Sketching the graph of a tangent function in the form y equals tan of b multiplied by x takes c. Here we must first plot out the important points of a basic tangent function, that is, the x-intercepts and the positions of the vertical asymptotes, and then apply the given transformations to these points. We can then connect these transformed points with smooth curves. Question type 3. Finding the equation of a graph of a tangent function. Here we need to find the values of b and c such that the given tangent graph can be modeled by the function y equals tan of b multiplied by x takes c. To find these constants, we can make use of the following rules. B is equal to pi divided by period, and to find c, we need to identify how the graph is being translated from its original position, also taking into account how the period has been affected. Finally, we applied these techniques to answer some exam-style questions. And that's it for now. See you in the next video.